and I'm very, very excited to host Professor Eva Agapaki, AI assistant professor at University of Florida. And it's my pleasure because I've been reading her research paper, and it's quite interesting work. And I thought it would be great if we can have a discussion around this topic. So thanks a lot for your time, Professor Eva, for this interview.
Thank you, Mayur, for inviting me, and thank you for the introduction. Hi everyone. I will start with an overview of the research. Before that, I just want to give you like a little bit of background of who I am and my path so far. I'm an assistant professor at UF and the director of the Digital Twins of Infrastructure Systems Lab. So we will talk about digital twins and AI today. I have a background in civil engineering, a master's in geotechnical earthquake engineering, and a PhD in engineering. All of that started in Greece, where I come from. That's where I graduated as a civil engineer, and I was always curious about research. So I started working on mathematical models to define earthquake-resistant infrastructure. And then that led to my specialization as a geotechnical earthquake engineer. But I was always fascinated about new technologies and how we can apply that to our profession. So I wanted to contribute more and have a substantial impact on how technology can influence our field. So that's what led to my PhD starting in 2016. So the goal, as we will see, is how to digitize existing industrial facilities. And we will see some of that today. And then my research was funded by the National Academies of Engineering, where I went to MIT for a year in the computer science department there. And then I worked in industry as well as an innovation lead. Yes, Mayur?
No, I just wanted to say, like, you're currently not sharing your screen in case.
Yes, I
Okay.
wanted to give just an introduction first.
Oh,
Um,
perfect, perfect. I thought like you were like clicking next slide, so no, my bad. Yeah, sorry.
no problem. Um, as I was mentioning, I also worked in industry as an innovation lead and engineer on how we can apply these technologies in manufacturing applications. And I've also worked as a consultant for other firms to advise them on advanced technology solutions. So we'll start with some of the projects. I'm now starting sharing my screen. Okay. So we will see today some of the applications of artificial intelligence or AI for infrastructure digital twins. So first of all, I would like to define like what is a digital twin, particularly for existing assets. So it is a digital copy that is connected to its physical counterpart throughout the life cycle of an asset. And given that the digital twin market is expected to grow up to 48 billion, but by 2026, that was a big driver for my research. So a digital twin can be defined at multiple levels. So at the individual object level, at the assembly level, or at the asset level. And of course, we can have even an ecosystem of connected twins, like for example, as a transportation network or a smart city. But in order to get there, when developing a digital twin, there are multiple maturity levels that we should consider. So a digital twin can have multiple meanings for different people. So I developed a framework where we start with a static twin that only includes the 3D model of the asset. And then, of course, 3D models are not always available throughout the life cycle of an asset, but particularly for legacy assets as well. So many times we need to start with what we will see today as the geometric digital twin that accurately reflects the as-is conditions of assets. So after we have defined that, we will continue with what I have mentioned as a foundational digital twin, which is essentially data-driven, and that includes multiple data sources and can also interact with humans. And that's also a very important aspect. So after developing that digital twin, the foundational digital twin, then we would be able to simulate future scenarios with the adaptive or planning twin. And finally, after we have all this wealth of information, that's why you see that here is a funnel, we can improve human informed decision making with the generation of intelligent twins. So, with that as inspiration, I wanted to show you what are the different stages in order to generate and maintain a digital twin of infrastructure systems. So we start with the physical asset, and the first step of the process is to understand the geometry of that asset. So this is done by using images, laser scan point cloud data, or depth sensors. And then we have the geometric digital twin, where with computer vision or deep learning algorithms, we use those to process the data efficiently, extract meaningful information. For example, the most important classes of objects, as we will see for some of the use cases. And once the geometric digital twin is created, then we have the operational twin that gathers all additional sensor data that reflect the current state of the infrastructure and can also predict its deterioration, as well as the response under extreme events like natural disasters, using time series predictions and a combination of data modalities. Finally, given the existing geometry and operational data, a generative design twin can be created, which captures in real time retrofitting operations and changes across the life cycle of an asset. And here we can use optimization techniques to automate retrofitting process. So with that, I want to share with you some of the digital twin implementation projects that I'm currently working on or I have worked in the past. So the framework that we saw earlier can be applied to multiple types of complex assets, such as space assets, bridges, manufacturing industry, industrial facilities, airports as well. And of course, the nature of the intervention that we need to make with a digital twin differs depending on the type of the asset. So whether it's a greenfield or brownfield asset, as well as the type of the project, whether it's a horizontal or vertical project, the scale of the application, so whether that refers to a product, a process, or a system, or an asset, or even a national or a smart city twin, as we saw in the beginning. And then, of course, where we are in the life cycle stage of that asset, whether it is in the design and construction process, its operation, or later on, even its demolition. So the clear problem that we have today is that all the legacy assets that exist are deteriorating. And this is exacerbated since current investments, and particularly in the US, are not enough to meet those needs. So there is a 2.6 billion investment gap, according to the latest ASE report card. And in addition to that, most of these assets rely on existing designs as well as documentation, which is not up to date. So as a result of that, we saw earlier that we need to have those geometric digital twins that accurately represent the conditions of an asset. These assets are heavily impacted due to yearly disasters, which can be either natural or man-made, and this incurs additional financial losses. So let's see now, as a first case study, how we can apply geometric digital twins for industrial facilities. So I use this matrix for all the use cases that we will see today. So that consists of like, what are the data sources that are needed? What are the KPIs, the standards, as well as the AI tools that define those digital twins in every industry vertical. So in terms of data requirements, I group them into these 6 categories. So we have geometric, financial, operational, drawings or CAD, and then even social and environmental data. So starting with geometric data, we can collect photogrammetric data or 3D data using laser scanners or LiDAR scanners, as well as UAVs or satellites. In terms of financial data, We would also need to think about economic downturn, budget reductions, or inefficient funding allocations, and these needs to be reflected in the digital twin. There are lots of sources of operational data, such as inspection or maintenance reports, that need to be reflected, as well as environmental data related to wildlife that can affect the industrial twin, the water quality, or even extreme events like natural disasters. So, given all these multimodal data sources, how can we process and curate those data sets? So this is where AI comes in. And here I summarize into three categories the most important tools that we can use in order to generate an industrial digital twin using either computer vision, deep learning, or reinforcement learning. So starting with computer vision, as a recap, that would refer to automatically identifying patterns in the visual data that we have. So for example, how we can detect objects, how we can understand the industrial scene, or even identify symbols in documents. Then we also can use deep learning, where we can process data in real time, or even image and video data. And then lastly, reinforcement learning, where we can analyze time-dependent data or allocate resources or materials optimally. Once we have those tools, then we also need to have specific KPIs to measure the value that the digital twin will have in the industrial context. So I have grouped them into four major categories. These are fidelity, cost, safety, and CO2 emissions. And finally, since at the moment about 95% of the data that is produced during the life cycle of an asset, especially during the operation phase, is not used, we also need to comply with the existing standards, for example, plant maintenance or building information modeling standards, or even documentation, to make sure that this information will be valued and important for the owner operators, or even the users of the twin that we develop. So with that, even when we have this framework, how we can actually start in complex assets like that. So assuming that we have access to laser scans of these assets, but not information from prior building BIM model. So how would we know what needs to be automatically captured in the digital twin? So in that context, some of my previous work has looked at what are the most important objects to automatically include in a digital twin. So there are only a few general categories under which industrial object types fall. So these are structural, electrical, architectural, equipment, safety, instrumentation, piping system, HVAC, or civil. And the approach that we would use for that was a statistical analysis to identify the object types that most frequently appear in these assets. So we would count the frequency for each object type. And then once we have those most frequent objects, like in this case, for in an industrial context, those are cylinders, joints, like elbows, valves, I-beams, angles, flanges, and channels. These roughly constitute 75% of a facility on average. We also need to know what is the time, what is the effort to actually model those with the current processes. So what we would also need to do is to capture the current labor hours. And in this case, for these particular objects, this is a data set that I developed. And based on that, I have a framework for the geometric digital twins of industrial infrastructure. So starting with a laser scan facility, then we would need to intelligently parse the data into smaller groups that have similar geometric relationships. So in this case, like what are all my cylinders, what are my valves, what are my elbows in a plant, and then from there to individually identify the objects that will be helpful for the generation of the geometric digital twin. Of course, we need to have some metrics as we discussed. So in this case, we're measuring the accuracy, of course, based on a benchmark that a human has created. So in this case, we see 80 and 70% separately for each of these processes. But of course, this is a complex problem, and we here we use deep learning methods to tackle that in conjunction with some other unsupervised learning methods based on the geometric properties of each object. So it is not just a black box deep learning method. It uses the contextual information from the specific object types that we see here. In terms of the applications of this framework, so it can be generally applied to these types of industrial facilities, starting with processing units, warehouses, oil refineries, petrochemical plants, with the intent to help designers and modelers to improve their BIM processes. Now we move to a different case study that I'm currently working on in terms of defining the airport digital twins for resilient disaster management. So, acting in a resilient manner is a really important topic, especially when it comes to airports, which are such complex systems. Again, looking at this matrix of data, KPIs, standards, and AI tools that are needed to define the digital twin of these assets, I group these into the same 6 data categories that are needed. And I have highlighted in red the data points that are different from the use case that we saw before on industrial facilities. So here, what is also important at an airport context is that we need to stress test the system, not only with internal data, but also a lot of external information as well. So, for instance, disease outbreaks, attacks, either biological or cyber attacks, demographic changes, as well as external political influences. And of course, some additional information related to the operation of the airport, which is related to the flights, of course, and baggage handling data, for instance, and occupant information. Given the multimodality of the data sources that we have, I have grouped here the 3 main categories of AI tools that can be used. So, for example, we can have deep learning algorithms, particularly the supervised learning algorithms, to model occupant behavior or energy consumption, as well as prediction of natural hazards, which is very important for airports, as well as NLP algorithms, particularly from the maintenance standpoint, as well as their inspection reports that happen daily in airports. Finally, in terms of optimization, since as we discussed, an airport is not operating in a vacuum. There are a lot of occupants. There is a lot of research that has been achieved in how we optimize transit routes, as well as passenger wait times, with some implementations of digital twins for airports that are just starting to emerge. And finally, in terms of standards, I have grouped them into 3 categories, starting with safety, environmental standards, as well as risk management. So with this in mind, I have developed a resilience framework, which I'm going to test with internal and external data stressors. So we can see here the airport performance on the y-axis, and on the x-axis the time. So we have 4 states: the planning state, disruptive state, recovery state, and the new steady or adaptation state. So right after a disruptive event happens, there will be a period of disruption at the airport. So and then the airport will either gradually recover or temporarily recover or not recover at all, depending on the intensity of the event. And of course, the readiness of the system to be resilient under such events. However, with the digital twin framework and having all those systems integrated together, we expect to have an earlier and smoother recovery to the new steady state. And lastly, I'm sharing with you another research project that I'm currently involved in terms of defining bridge digital twins for their infrastructure, better infrastructure management. Again, with the same framework that we've seen in terms of the data requirements, there are some additional requirements related to maintenance planning, such as the bridge inspection reports or other like load rating reports that reflect the capacity of the bridge, as well as social data, for example, from traffic. And for specific bridge types, we would need to look at, for example, scour and water quality for certain types of bridges. And some AI tools related to the generation of bridge digital twins that are related with deep learning, for example, the ESIS geometric digital twin that we saw in the beginning, or NLP to extract information from these inspection reports or work order prioritizations, and finally, generative adversarial networks that are used to predict the capacity of the bridge. There has been a lot of work in that area. And finally, in terms of standards, a really important aspect is maintenance, as we saw. So we need to comply with, so everything we develop that is related with the digital twin needs to comply with existing uh, Federal Highway Administration manuals, as well as the respective Department of Transportation manuals and other manual processes related to the inspection of those bridges, as well as the safety, of course, and the capacity, the load carrying capacity of the bridges, and finally, risk management, which is currently in the systems or in the bridge management systems that we need to comply with. So these are the projects I wanted to share with you. And here my information if you want to learn more. So I will now stop sharing my screen and turn
I,
back to you.
I must admit, like, big round of applause, like, great work. It's so inspiring to see all the thought process, the framework, and the case studies you shared. Really commendable.
Thank you. Thank you.
Yeah. So, Professor Eva, you talked a bit about your like journey, your interest, your curiosity about behind the research, and can you talk a bit more about what are some challenges you faced in your PhD research?
One of the biggest challenges was related to acquiring data from these infrastructure assets. And not only acquiring the data, but also preparing it in a format that is compatible with current tools. So that was a process that was not straightforward, that it needed a lot of understanding of the data first. And then based on that, to see what are the capabilities of the deep learning algorithms that were needed to be used. And it was a process, it was around that time that, because of the nature of the data, like the 3D capture data, that the initial algorithms in that space were developed. So there was a lot of work that needed to be done. Now it is this field of research is a lot more mature, but still there is a huge curve in terms of being able to use those algorithms for processes directly, as we use, for example, image recognition tools that have become like a commodity. So there is still a gap, which I think it stems from proper data collection, data annotation efforts, and as soon that's resolved, I think we will see huge improvement and a lot of advances in that space. So to summarize, that has to do with like all the geometric digital twinning development challenges that I faced.
I see. And just to set the context, like, what was the year you were doing this experiment and research, so like people can know?
Right. So that was I started in 2016, and that was like the first results that I had were in 2018, 19. But I'm currently still involved in that research. So it hasn't stopped.
Nice. Because like in AI, like every day, every week, there is like new models, and a year in AI is like feels like 10 years based on the research. So that's why like the same model in 2018, like now there are like different versions or something. Yeah.
Exactly. And that I wanted to add on that, for example, that in our community we can leverage all these pre-trained models that exist. Um, of course, they are more general, like in the at least from, let's say, for the computer vision community, more general objects of not so specialized, like the ones that we need in our profession. But there are some efforts, like for example from Design Say, the Structural ImageNet, the Data Center Hub, that have started creating those data sets, and we also see those progressing for point clouds. Like just in the last weeks, I saw like a paper being released on like synthetic and real point clouds of cities, and that's all available, publicly available. So there have been a lot of advances in that space, and we will see a lot of improvements as we move forward.
Got it. And I'm imagining when you were doing this in 2017-18, there might not be a lot of precedent of geometric digital twin using AI. So, what were some precedents you would like to suggest to people and advise to researchers who are currently interested in this area?
Exactly. So now I think that the resources are definitely many more than the years that I started looking into these problems. So my first advice is to look out of the box, to try to think and look at solutions out of your out of your discipline. Because, for example, like in computer vision or natural language processing communities, there have been a lot of recent developments in these networks that you would need to understand. And in order to do so, by reading papers, collaborations with researchers in these communities, will nurture these like speaking the same language with them effectively, so that they can also understand the value of these problems for our field. So I think that's the first advice that I would give, and then to look for simple solutions first, not always like trying for the most complex network, or just to to show that it's the most complex method because we are solving engineering problems, and starting with a simple solution first and then building on top of it. That's another advice that I want to make sure that is shared.
Yeah, is there any particular group in computer vision and natural language that we can like relate more who are doing research? Uh,
So in computer vision, there is a community, and particularly conferences like, for example, CVPR and ICCV, which are the top conferences in the field. This is where researchers from the computer vision community will come together, and sometimes there are also some sessions organized related to our built environment. And then in terms of general machine learning and AI, NeurIPS, ICML, and iClear are some of the conferences that I would recommend following, because they also have some applications in different fields, but there will be soon, I believe, in our civil engineering, structural engineering communities. And
yeah.
I'm also organizing a special workshop this summer, actually, related with computer vision and cognitive machine learning for resilient infrastructure.
I highly recommend everyone to check that out. We'll link that in the description as well. And Professor Eva, can you share some examples of applications of AI in civil and structural engineering apart from like geometric digital twin?
Mm-hmm. Yes, so there are multiple applications. Like for example, like we discussed in computer vision, like damage detection or like corrosion that is very important for offshore like infrastructure, and then structural health monitoring of bridges is another one. Or if we need to identify like soft stories in buildings. So these will be areas where we need to apply either supervised learning methods or semi-supervised, where there is some also not only the need to have like such huge labeled data sets and tasks related to, for example, image classification or segmentation or detection. So these are some of the top areas of application in that spectrum. And with regards to NLP, for example, information extraction from building drawings, reports. There are so many data sources, of course, that need to be consistently processed to create those data sets first, and then being able to apply all these tools that have been developed in sentiment analysis and information extraction and all. There is a lot of interest currently for transformers in both language and also vision tasks to be able to focus on specific parts of the text or specific parts of the image to extract information more efficiently. So these are some of the applications that I see.
Yeah, there's a lot more applications to be developed like in this area, and it's just the beginning of our field. We have a question from Steven. Can you speak to some of the data formats and workflows that support long-term viability?
Um, so in terms of like, of course, like there needs to be the platform, the digital twin platform that supports that, and it depends on the format of the data that we want to ensure. Like we can have like different converters from like different types of models if we want to use 3D models, and then aggregating those like in data lakes, for example, as well as like if we want to use like text, there needs to be some conversion there for the algorithms, but these should be separate. Like the data lake should be separated from all the processing that has to be done in the algorithm, the deep learning development part. So to keep that consistently, and versioning of the data as well as the pre-trained models and the algorithms. So yeah, that would be my suggestion there.
Got it. So we talked about research and how academia, along with your use cases and case studies, are using AI in the research. What are some low-hanging fruit which the profession can adopt from research or from pre-trained or developed models out there?
So that's the first low hanging fruit that I see would be to not start like developing new tools, rather to make use of the existing tools by either using like their pre-trained models and then making adapting them to the specific problem. Of course, with some always with some human verification in the end, because we are looking at problems that we need to clearly quantify the uncertainty as well as the accuracy, which is really important for our applications. So that's an important aspect, to not just having a black box, but always to have a human to verify the result in the end. So that's the first one that I see in terms of immediate and a quick adoption to leverage all the existing platforms and tools. And there are a lot of those from like different like technology firms as well as open source tools available from the research community. So the first is that, and then what is the second low hanging fruit application that I would say is related to like any advances in subfields of like computer vision and NLP to be able to look at the most prevalent tools that can be easily adopted to these problems. Of course, based on the specific data requirements and the user requirements that we have, but not starting with, as I mentioned, like complex solutions or starting from scratch, developing tools that already exist in other communities. So making sure to do like a proper research across what's available, and there are a lot of tools at the moment available before going into like from scratch development.
God. I have this like personal question. So like back when I was a structural engineer, like even like it's a high risk job. Like the analysis or
Yes.
assumption you do has a impact in the building and people's life. And I see AI in architecture, which has like more generative and creative, which is have lesser risk than AI in structures, which like if it's in structural health monitoring, it has a lot of implications. So like how do you like manage the risk appetite or like ensure it's accurate and like uh, people who are using that AI for structural applications know the implications?
That's a great question. So the part that I think is really important is the so-called like human in the loop, which always needs to be embedded in any type of AI ML application in our field, because we cannot simply rely on the end output of these tools. We always need to have humans and operators to be working in parallel with these tools. So a large part of my research currently is on that, to be able to have that human in the loop engagement, which will also quantify, for example, the subjectivity of not only the humans but also the AI algorithms. And another part, another part that I think is really important is in terms of explainable AML model. So to be able to use tools which we can interpret, for example, their features. And there are some of those like XGBoost, for instance, algorithms that we can see like how which are the prioritized features that we can use and interpret them, because that's a part like we like as engineers we need to know what is behind the scenes and of the developments of these algorithms. We cannot just rely on an automated result and completely ignoring the human aspect of it. So these are the two elements that I would be focusing on.
I see. Yeah, that's a great point. We have one question from Luke. How do you think that we merge the information from laser and camera to improve the semantic understanding when we use digital twin, for example, 3D segmentation using deep learning?
Great question. So, in terms of merging information from laser scans and 3D models, that's an area where, like, for example, we would need to have those in the same data format, like either converting the model to a laser scanned representation or the reverse. to be able to use both when we need to use segmentation models, because we cannot use both resources in their respective formats like IFC and then laser scanning models. We need to convert both in like if it is a laser scan survey, it should be adaptable with a 3D model representation, or the opposite. Otherwise, and there are algorithms for both. Like if we need to merge and interpret information in IFC formats, that there are algorithms that we can use to learn these representations directly. Or if we want point clouds, then all the research related with the 3D geometric learning data. But we would need to decide based on what are the requirements of the project, or if it's just comparison of the two. Again, we would need to have the same data format.
Got it. And based on your experience, like, can you recommend some tips or best practices for ML-based geometric digital twins?
Yeah. First of all, it comes to getting good quality data. So if we have like errors in terms, like for example, registration errors or incomplete scans, or not a representative data set, then all these will be reflected on the output that we get. So we need to, as I mentioned earlier, to get to know our data sets really well, and making sure that there is a quality control before we start even the AI model development. And that is a best practice that I have seen in terms of the data collection part. In terms of the processing, it comes to deciding the best way to, like I would highly recommend using all the cloud services that are available nowadays for fast and efficient processing, especially because of the nature of these 3D data sets. Definitely the use of GPUs, but in some cases, this is not a possibility because of the security issues that are reflected with these types of data sets. So there would need to be a solution on-prem as well, to be able to alleviate these types of issues. So having that type of flexibility. And then with respect to the algorithmic development, as I mentioned, that first of all needs to be driven based on the data and the data requirements and what is the output that we want to achieve. If it is, for instance, just a segmentation part that we want to identify and analyze specific parts in the scenes of the point cloud for like safety applications or like modeling applications, then there are tools available, especially in the building scene with my research in the industrial scene, and also there will be soon in other domains, which need to be leveraged. And there is a portion of research that has to be done in terms of efficiently creating those data sets, either by using synthetic data. And there is a little bit of analysis that we need to do there in terms of what synthetic data is useful and how we generate that, but that will help alleviate the problem of the huge amounts of data that are needed in this space. Other forms of research that do not need that huge amounts of data, like semi-supervised learning, for example, are in very early adoption stage. So there will be a lot of research to be able to prove the validity of those tools. Um, and then finally, when it comes to the actual delivery of the results and the implementation, to be able to have like proper infrastructure to be able to disseminate, to interpret the result. Again, like going back to like the explainability of the models and how we can engage the actual and validate with the actual users that this is indeed the outcome, and defining the value for them based on the metrics. So that's these are like some from my personal experiences as well, best practices that I have captured.
That's great. And it this might be very subjective. What is a good thumb rule for data collection? Like how many objects? Like there might be a new structural element. What's your suggestion?
So, in general, we need to have a balanced distribution of our data sets when it comes to the learning part, the training part for these algorithms. So, if we have a particular like objects class that is very highly represented, like let's say all the positive examples occupy like 78% of the data set, and then we have all the like 20-30% of that of the negative classes, either images or point clouds or any ML data set, then the output of our algorithm will be biased towards the positive class. So we always need to make sure that that goes back to my earlier point of like looking at our data distribution and understanding our data set and the needs that we need to have, because in many cases, like for example, when it comes to damage, we won't have so many damaged areas as like the ones that are not impacted. So we need to make sure to include either to synthetically create the remaining data points that we need to have that balanced distribution, or to find ways to fine tune our model when it comes to the learning part, um, to be able to account for these differences in our data sets.
Got it. And are there any particular algorithm one should use for data distribution analysis?
So that comes with like doing data analytics on your data set, like what is the number of your images for a specific class, for example, what is the number of your objects, in like if you want to identify like let's say cracks, you have like thousand of images of cracks, but you have like only 50 in terms of like identifying like potholes. This is not a balanced data set, so we need to make sure that we have equal distributions of those. So it comes just to analyze like some statistics and a statistical analysis and packages. Like for example, there are many of those in Python, sklearn tools packages, for instance, or even R. If some researchers use R for statistics a lot, so there are built-in packages to do this, and also having distributions to visualize your data sets as well.
That's great. And my next question is, if you had unlimited time and resources, what are some research topics or models you would like to experiment?
So, in that case, like I would definitely want to stay in um, generating digital twins of infrastructure, but having this dream of like doing that in space. And that started actually because I recently got funding from an organization related to NASA. So I have this dream of like being able to actually see that implementing such constraints and these conditions, the challenges that are related with development in space. So that would be definitely the priority in my research agenda, to be able to tackle that.
I see. I'm just curious to know more about it. Like, so it would be like a whole new materials you need to deal there, and like the fabrication side and the construction, which will go into the model integration.
Mhm. That's right. So there are there is this human in habitation on Mars, for example, and some research projects that are currently running in that area with new types of construction in terms of developing these platforms there. But when it comes to like actually capturing the conditions given all these threats and simulating this in advance, given the constraints and the differences uh, from what we have here on Earth in terms of the conditions, it's like even the sensors, like being able to operate without having without even having us as humans to correct those errors when they come, as well as the precision and the accuracy related with what needs to be developed there.
Yeah, that is quite interesting because like I haven't seen any like structural health monitoring data or time series data of building performing in Mars. So like there like I don't know like if there is a non-linear analysis formula for doing that, or it would be data driven AI analysis if you're designing for Mars.
I think that like that would need to be like a hybrid approach with both ML as well as experimental empirical models to be able to do that accurately.
Got it. And you mentioned about conferences. Are there any like online courses or any like so you mentioned about the summer school which you're teaching. Anything which students who are interested to learn can attend AEC specific?
So there are a couple of online sources, like in all the platforms that are, for example, related to more the deep learning AI side. Like there is an appearance of those. I would look for like the workshops that are currently starting, or like the specific conference tracks for conferences in our domain. And in terms of online sources, I don't have specific ones for the AEC domain, but I would recommend like getting familiarized with the tools, with simple coding platforms like in Google Colab or Jupyter Notebooks, to start the journey like with as simple as possible, and then transferring that to our field. Of course, there are. I would recommend like for the researchers to look within their university. I know there are some efforts by AAC to have like some trainings related to AI and ML. Specific universities like at UF, we have all these trainings related to AI, open to all researchers, as well as the specific domain knowledge and courses we develop, particularly for AEC students to attend and learn with applications on in our field. So I would look. I would recommend doing a research on these platforms.
Got it. So I'm just amazed. Like, so you have structural engineering background, you are doing AI research, you're teaching workshop, teaching courses, and doing research. Like, what's your time management secret? Like, how does a day in your life look like?
Uh, so it is. It is. It's so that secret is still under development for sure. um, uh, but I try to have like specific time slots for specific tasks and trying to set deadlines for myself to be able to finalize certain tasks. I'm very results driven, so I usually have like my own deadlines in addition to all the other deadlines that are happening to make things work and move forward. But I am a strong believer of having like a balanced life and having time to invest on personal time as well. So I'm working on that too.
Got it. Before we move to rapid fire, like, is there anything which we didn't cover in this interview but you'd like to share?
So the only part that I wanted to like close that this interview is related to like to not being afraid by like even if in our community maybe it's not that we had like the background or the education to work on these tools, but it's not a path that it is not accessible to us. Like to not being afraid to explore, to try out, and being patient because there will be a lot of code bags to solve, but being patient with it and trying to, as I said, engaging with the communities that are developing these tools is definitely beneficial.
Yeah, a lot of times there is a code error and then you get frustrated, but still like keep
Mm-hmm.
doing because that's part of the learning process. I could totally relate. So, the last segment is this rapid fire. You'll have 10 to 15 seconds to answer, and you got to keep it very brief. So, let's do this. Uh, Places in your travel bucket list.
So I would like to go to Australia because of their familiarity with digital twin technology at the moment.
Got it. Any book which made a big impact in your life?
So that was a deep learning book by Ian Goodfellow, and that really changed my perception in the beginning when I was learning like machine learning and AI.
Got it. Your role model.
That would be my father, who's always inspired me in terms of choosing this career and starting as a civil engineer.
Oh. Your favorite research paper or model till date. This is gonna be very tricky.
Um, so I think I was amazed when I first discovered the 3D geometric deep learning papers, and particularly PointNet. That was really instrumental to me in terms of the capabilities.
Got it. Uh, what do you think are key challenges in AI adoption in the industry?
Integration. So integrating all these new tools and technologies we discussed with computer systems that may not be up to date.
Got it. And is there anything in your life you wish you would have done differently?
Um, So I would probably focus a bit more on entrepreneurship. I think I always had like this entrepreneurial drive, but I would like to start like that earlier in my career.
Yes. What's your favorite movie?
Um, so that I need to think about that more. Um, um, I mean, there are so many, so I think I wouldn't be able to choose from.
It's totally fine. Uh, and lastly, let's make it simple. Your favorite restaurant.
Uh, so any Mediterranean cuisine restaurant.
Got it. I think this was quite insightful. Thanks a lot, Professor Eva, for your time. And I look forward to your research and thanks for sharing all the work you're doing. And for people watching, Definitely check out the summer school.
Thank you, Mayur. What a pleasure to be with you during this hour, and wish all the best for this podcast.
Thank you. Have a nice rest of your day. Bye.
Bye bye.